Hello, good day. Welcome everyone to the stream. My name's James. I'm one of the founders and Chief Technology Officer over here at Topl. And welcome to our live broadcast for today. So in this broadcast, we're going to begin to explore Topl's extension to the UTXO transaction model, which was popularized by Bitcoin. And we're going to explore, or specifically, we're going to explore how Topl extends this model into what we call the IO transaction model. And this IO transaction model is how we structure our ledger updates, mutations. So it's really critical to, having a thorough understanding and really having having everything set in stone and well communicated. So, like I said, it's probably going to be the first in a couple of these because I'm going to try and take it a little slow and start from basics. If you have any questions at any time regarding, what I'm going over, apologies, what I'm going over, or if I'm going too fast, then please feel free to drop it in the chat. All right, I'm just going to plug in the computer, and also apologies for any folks that were waiting on the dead air for a little bit. There's some technical troubles with secure wireless networks and iPads, so apologies for that. But yeah, otherwise, I think we're just going to go ahead and hop into it. Alrighty, so as I said, we're going to be specifically exploring the IO transaction model today. And this is specifically an idea of, like I said, extending the UTXO data model with an eye towards, cross-chain interoperability. Hopefully I can convince you all that this IO transaction idea it's a very minimal set of assumptions at the highest layer. And so the possibilities there, or the desire, is that then we can get greater adoption or a mutation. We can map other chains into this similar model, this very simple model, and then, like I said, we can facilitate cross-chain interoperability. Just for reference, a lot of the models and things that I'm going to be going over today are available in our GitHub, specifically under github.com/Topl/protobuf specs. We do use protocol buffers, which, if you're not familiar with that is, don't worry. This is a bit for the maybe developers out there who might be tuning in. So we do use protocol buffers to do our model definition. And specifically today, we're going to be exploring under this Bramble models and under transaction. And we see this IO transaction. So we're going to be exploring some of these things today. So just a bit of a preview about where we'll be going. But yeah, it's a bit, let's take a step back before we really delve into that complexity. And really the first thing I want to explore with everyone is, I'm just going to try and make it very high level today. Oh, well, sorry, I thought I should have put, there was a third thing or something right above this that, what is UTXO? So if anyone's unfamiliar, we're going to spend a little bit of time talking about the UTXO model in general and why, or how it functions. Then we're going to talk about how can we think of transactions and how do we think about them in the Topl ecosystem. Okay, so first off, so this is a great diagram from a Medium post going over the comparison between the account model and UTXOs. Highly recommend. I just copied it from somewhere else. So But you can see that the idea behind UTXO, I guess I haven't defined it yet, is it is an unspent transaction output. And that unspent transaction output can be, so you see this, we have transaction 0 here on the far left. So there's inputs and there's outputs. In fact, we see this thing called input 0 and output 0 and output 1. But then we have this arrow where this output 0 is, somehow is connected to transaction 1, and that output 0 is connected to this thing we call input 0 in transaction 1. So if we, to reiterate, transaction 0, output 0, the language we use is it is consumed, or the language I use, because I think it's useful. It is spent or consumed by transaction 1 input 0, right? And that's what this arrow references. And that idea of consumption, or like consuming a reference, is pretty much the whole basis of the UTXO system. This is a little bit different than the account model. And if there are questions around that, I'm happy to explore. But I will reference that there's a really great talk that I gave to, or I say really great, but it was a good talk, invited talk from IOG at their Scottsfest back in November of last year, where an alliance that Topl we're part of called the UTXO Alliance, we are promoting these ideas of how to use UTXOs, in comparison to the more prevalent model that's dominated so far, which is the account model. So if you're interested, I'm happy to pass this along. We have a whole group working towards trying to evangelize. And yeah, if you're interested in that, please, we have a Discord and Telegram channels and that sort of stuff. So happy to pass those links. Okay, but back to this picture. All right, so we have several different transactions here. We have 1, 2, 3, 4, 5, 6, 7. If we say with a 0 index, and really the only UTXOs in the system are in this whole diagram are transaction 6 output 0 and transaction 3 output 0, right? Because those are the only two things in this diagram that aren't consumed within this diagram. So if I were to package this whole set of transactions as like a single, if I were to kind of zoom out and say, what is the net effect of these 7 transactions? You might just say, well, there's input 0. I came in with 100,000 Satoshis, and I went out with, because it should equal 100. Why am I not accounting to 100? Well, anyway, sorry, I should have, before I said that part, you should be able to zoom out and see that there's a, like a net effect of this. And I'm sure if I spend the time, it should be a rule of Bitcoin, the Bitcoin ledger, is that the sum of inputs has to equal the sum of outputs. And so we see here, we can just see that in transaction 0, that the 100,000 Satoshis in, there's 40 and 50. And so we would assume from this diagram, because the restriction is that the sum of inputs has to equal the sum of outputs, then the 90 here, that difference is made up by the fee that must go to the pay. It's either burned or paid. So I guess if 30, so there's another 10 taken up there. There's a 20 and a 20, so there's another 10 taken up there. There's a 10, so there's another 10. There's 10 out of 20. So yeah, actually that's where it is. So yeah, all 7 of these transactions paid a transaction fee of 10,000 Satoshis. And so that reduced the original 100,000 down to 30,000. And then we can see, there's a 120K and 110K. So that equals 30. And then this would be 40, 50, 60, 70, 80, 90, 100. So this picture is like valid. in the sense of a Bitcoin ledger. But hopefully I haven't gone too fast. But this is what I want to show here is this idea of a UTXO graph or a transaction graph. I kind of use those terms interchangeably. In particular, we can see that these things form a DAG. Now, DAGs stand for directed acyclic graph. And a directed acyclic graph means that there's no cycles. It's acyclic. And the directed part, that there's parent-child relationships. I don't know why I kept trying to say parent-child relationships. So these that directedness, you go from one and it points to another, and that's what I mean by parent and child. And you never go backwards. So with this idea, and that's exactly what we see here, right? You always go from left to right. I do see we have a question in the chat, so I'm gonna pop that up. Oh, cool. Yeah. Thank you, Liam. I'll leave that up while I answer. Yeah, there's actually a lot of chains that the UTXO model could be interoperable with. Really, I said I'm going to go super deep into it, but we can think this idea of most chains will say they're either account or UTXO, but this idea of account versus UTXO kind of doesn't really encapsulate the whole picture, because there's kind of two components to those two things. There's the data structure, the actual way you organize, and there's what I think of as the state mutation policy. And that's a weird word or weird thing to think about, but it's where MEV comes from in Ethereum, because you don't directly sign your outputs. And that consequence is, what I call public state mutation versus private state mutation. You could do a UTXO system with public state mutation, right? You could have the data structure of just like a flat hash map with a public state mutation, or we could flip it, right? We could have a private state mutation, like what's commonly used in UTXOs, but we could instead of having a flat hash map, we could structure it, those UTXOs, into an authenticated data store, right? And that authenticated dictionary can be used to help us actually identify particular sets of like the UTXO sets, instances, versions of the UTXOs, the entire UTXO set. Okay, so to come back to your question, Liam, about interoperable, this model will be easily interoperable with other UTXO chains, assuming they can satisfy the constraints of the structure of the transaction, as we'll get into in a second. Account models might be a little more difficult, but it's not, I won't say that account-based things might be a little more difficult. And I would even think that, it's really interesting. There's been a lot of work lately in the Ethereum ecosystem to do account abstraction, because rollups and things are actually this idea of private state mutation really helps. I say helps, but it lends itself to statelessness much better. And that statelessness, I'm sure a cryptographer or someone who's more familiar with this might be able to provide more detail in this, but that statelessness really helps to be useful for cross-chain communication, and particularly ZK rollups, or like rollups in general. Because like I said, the statelessness is the state that you need to process the validation to actually know if this thing is valid is kind of it's all encapsulated. And that idea of encapsulation is one that UTXOs are really good at. Yeah, thank you for the question, Liam. Those are good. All right, so now that we have maybe a little bit of idea of what a UTXO graph is, let's break this complexity down a little bit further. I want to boil down and say, like, let's go this small, right? Let's just, I'm going to build up a whole, I'm sorry, I keep trying to figure out how I'm going to introduce this. One of the ways that I've started to talk about our system as of late is it's kind of it's a very heavy term, and I don't necessarily think people should understand it at first, but I do think it's accurate, and that's this idea of like a multi-dimensional or hyperdimensional time-ordered event DAG, right? And that's just a mouthful, right? A multi-dimensional time-ordered event DAG. You're just like, James, what the heck is that, man? So we covered what a DAG was just a second ago. It's this, if we boil it down, it's just a graph that has parent-child relationships and no cycles, right? Which is exactly how we spin, how we create these, or is exactly the system for cryptocurrencies and other consumable reference type ledger systems. But we haven't really talked about events, right? There are multiple types of events in our blockchain. Today, transactions are one type of event, so we'll focus on those. The other types of events that we're currently working with are blocks and epochs. Those are more concerned with the consensus side of things, so we're gonna we'll save those for another time. But then this other part, this like multi-dimensional time ordered thing, right? This is where it gets a little complex. And so I think let's just get rid of that for now. Let's not even think about that complexity. Let's just boil it down to the simple balls and sticks. I'm a physicist. I was like trained as a physicist. I really like spherical cows in vacuums, isotropically emitting milk in all directions. So let's figure out how to do that. Before I hop into this, maybe let's check if there's a question or if anyone has a comment so far. All right, so we're going to go down to one of those transactions we saw before, right? This is like transaction 0 where it has some inputs and outputs, right? That's what I'm trying to show here. And I'm going to say the input, I'm going to call as an unspent token, and it's this thing over here. So the unspents are on the right. They're the children of a transaction, right? They're the children outputs, the unspent outputs from a transaction. But on the left, the consumed reference, the spent output is, points to the child and is on the right. I'm sorry, on the left. So spent on the left, unspent on the right, and I just have a, this is generic transaction. So we'll see, we can give them numbers to order them in a second. This is, a very, very simple view of what I mean by a UTXO transaction or an IO transaction. Right? This is like the simplest way I think I could try to explain it. These tokens don't have any, like these are just literally icons. They're not, I don't have numbers with them. I don't have any, like, that's what we do here. We think of, okay, expanding on this idea of you can have a spent reference on the left that is consumed, a spent output reference that's on the left that is consumed and then recreated as an unspent reference. But those outputs themselves can have additional properties associated with them. For the sake of simplicity, this is where the multidimensional part of that thing I said a little while ago comes in. But for the sake of simplicity, we're just going to think about like these are actually really, this is the simplest system we could have, right? The only property they have is address. There's no number. There's no like numeric property to them. There's no label property to them. There's just, oops, my bad. There's just who owns it. Who owns this? And if you want to think of it as an NFT, yeah, it's just like who owns this NFT. And so right now, this is a transaction that takes an NFT and transfers it from A to B. That is one way of describing this this transaction. Okay, and I'll just go to the last one in the series and then pause for questions. But just like, just a little bit more complex, instead of moving a transaction that can only change, like supports one-to-one mapping, these sorts of transactions, UTXO transactions in general, can support many-to-many mappings. So this transaction is one where A was able to own 2 different tokens, right? We're not gonna, or if we want to really, maybe we do it this way. What if we do like B, like that? Because it's a, yeah, anyway. So here A has a token and B has a token. They each, partake in this transaction where B decides to send their token to C and A decides to send their token to B. And that, as this transaction has to be validated within the rule set of the ledger, right? That is very important. If you recall a second ago, when I was talking about this, I said that a rule in Bitcoin is that the sum of the inputs has to equal the sum of the outputs plus the fee, and that's an arithmetic constraint by Bitcoin. But really, you could have any. Like, what if I said I could make up an arbitrary arithmetic rule and say the sum of the inputs, the sum of the inputs has to equal the sum of the outputs divided by 2. Or it's the sum of the outputs, times 90%, and there's always a 10% fee attached. Like, basically, whatever any business logic you can come up with to put into the ledger, you can generally figure out a way to try to apply it to the state mutation, to the validation of state mutations. Depending on how much, it can get more complicated. It's not always going to be possible to do that, but I just want to point out that this particular idea of, within the rule set of the ledger, this is something that I've really come to appreciate in the last few months or so, because we have a really interesting asset model that allows for some rigorous, like, formal definitions of token behavior within a ledger. And so I think it's an open question and very interesting question to me to have state channels that can open and close that are based on only allowing certain types of tokens within that state channel. And those types of tokens define the rules for how to participate in that ledger. And it's now you've taken the behavior of the ledger update process and kind of embedded it into the process instead of having to leave it at the higher layer of smart contracts. So it's just pulling that token behavior down into the protocol instead of leaving it up at the smart contract layer. Smart contracts are really great for some things, but we can make the token behaviors much more efficient if we pull it down that way. Okay, I'm gonna pause one more time. Yes, thank you, Enrique. A, B, and C here are our addresses. I apologize. I should have. I kind of skimmed over that. So I'm just going to give this. So expanding on the previous view being this very simple one to the left. Tokens may have additional properties associated, such as an address. And then I should have said that A, we're just going to consider A as an address and B as an address. And without saying like what A and B actually correspond to as an address. An address in this sense is just like a way to locate, right? It's just a label for where to locate the token. Kind of like saying home refers to a specific address for you as a person. Are any other questions before I move on? Thank you. All right. Okay. So before I, sorry, one more time. Just in case anyone's just joining us, welcome. I'm James. I'm one of the founders and the CTO over here at Topl. And today we're talking about our IO transaction model, which is an extension of the standard UTXO data model that, and really, it's a small extension that is how Topl organizes their ledger updates to perform ledger maintenance across the blockchain. Okay, so this is kind of the representative view of just, these are what transactions are. So let's go see what we can do with them. So maybe it's a little hard to see, but down here, this is just, just a graph. Here I have some addresses. Oh, sorry, that keeps doing that. There we go. Here I just have some addresses, A through G. And I'm gonna, and at t equals 0, which is Genesis, right? That's just the time, when I start the blockchain. So you can think of in the Genesis block, I'm assigning a token to G, a token to C, and a token to A. And because it's at Genesis, they necessarily have to be unspent because otherwise they wouldn't be valid. So we have our little open circles here. And the rules of this ledger, like what I was just referring to in terms of the variation of the rule sets, are, let's just make that a little bigger. So ledger rules, tokens are distinguishable, meaning that I can't combine them. So I just want to say that they're distinguishable and may not be broken apart. That's just me trying to be formal and saying that these tokens, if we start with 3, we're going to end with 3. And I'm going to add the additional constraint that addresses may not own more than 1 token, which is why I changed this picture to not have 2 A's since it conflicted with this bottom one. But yeah, so hopefully this little setup makes sense. Right now these things go, there's a long time axis, but we're only looking at t equals 0 right now. Right, we're not looking at we're just looking at our initial distribution of where tokens are in this theoretic ledger. Okay, before I go on, make sure, we're good with this. It can quickly get more complicated, so I'm trying to make sure. Cool. All right, let's go. All right, so now we're gonna create transaction 0, and you see here though, compared between this one, now we have a new time t1. We can call this what is the token state, or what is the UTXO set? Who owns the UTXOs in the system, right? So here we might have asked who owns at t equals 0, who owns the UTXOs in the system? Well, A, C, and G. And if we go at t equal 1, well, t equal 1, there was only one transaction that happened between t0 and t1, and that was transaction 0. Transaction 0 seems to have consumed the G UTXO and the original A UTXO, or the T0A UTXO and the T0G UTXO. And it transforms it, right? This G1, G sends theirs to F. So this is the new UTXO. C wasn't involved in transaction 0, so they just move along. They stay, their tokens just stay where they were. And then A sent their token to B. So we're not talking about this is purely a diagrammatic. What I'm really the point of this part of the lecture is to think about the time ordered part of the event DAG of the description I said a little while ago. So if you remember, I said it was a multi-dimensional time ordered event DAG, right? So this is the DAG. These are very, very small DAGs, like 1-step DAGs, but technically you could call it a DAG. I think, maybe I'm wrong in that. That's what I get for not being a computer scientist. And then, yeah, we've already talked about the events and the multidimensional part. The multidimensional is just the fact that you can have multiple properties associated with a single thing. So it can have a quantity and an address and a label, right? Maybe it has multiple labels, that sort of stuff. And that's where the multidimensional comes. That what we're exploring now is the time ordered portion of it. Okay, to come back, recenter. Sorry for that little tangent. So we're seeing when the ledger is at T1, the UTXO set is that F owns a UTXO, C owns a UTXO, and B owns a UTXO. And that is, that is just following this one transaction 0, that had 2 inputs and 2 outputs. All right, still good to go. All right. Let's just go one more. This is where the iPad would have helped, because I was hoping to keep drawing on this. But so I took a little bit, couple more steps this time. So here I'd only done one transaction, but now I'm showing a couple of transactions. So we still have the original transaction 0 that spent G and sent to F and took A and sent to B. But now we have transaction 1 and transaction 2. Right? And transaction 1 takes what was at a UTXO at T1, and it consumes it, or it spins it. And what we don't see here, what we're not seeing in this particular view, if we had a slide between the two, we would see that at T2, G would own a UTXO. Right? I know it's not shown here because I'm showing this picture we have as what is the UTXO state at T2. I'm sorry, T3. My mistake. I didn't update this. Right. So I know I added a little bit. I jumped ahead a little bit, but I think we can all. I hope we can visualize. This would just be an open. If this wasn't here, this would just be an open circle, right? As with these other ones. So transaction 0 had 2 inputs and 2 outputs. Transaction 1 has 2 inputs and 2 outputs, right? But transaction 2 only has 1 input and 1 output. And that's why we can see that this one is a spent, and it's spent by 2, and it gets sent to F. But the unspent, right, the other unspent from transaction 1, which is owned by E, is not involved in transaction 2. Therefore, it stays at E. And similarly, after the first transaction, the token at B was never moved. So it just stays there the entire time. So the end result is the UTXO set where F owns a UTXO, E owns a UTXO, and B owns a UTXO. And really, it's you just keep going. That's what this is what DAGs are. Right? You can add additional properties to these things. You can have and once you add particularly quantity is a very interesting, and when I say quantity, number, just a number to it. Right now, these tokens don't have any data associated with them. The only property they have is what address they're at. But you imagine if I start assigning numbers to these, now I could combine them, or I might be able to split them apart. And so the complexity of this graph can adding or additional dimensions to it. But this is the first step. This is the base of it. If you can understand this, you have a very good foundation for adding the next layer of the next dimension. And once you kind of add a dimension coming in and out of the board, it's really interesting to think about how you can have arrows that go from one dimension across to another dimension. If that part didn't make any sense, don't worry. But it is a very interesting and intriguing concept. Okay. So now I finally explained, I think I finally gotten us through what I mean by, the multidimensional time-ordered event DAG. So I'm going to show you what it actually takes to make a transaction. Like, what is the construction of a transaction in our system? And because everything I've shown you so far isn't any different from the UTXO model. I've just been trying to be very, thorough in my definitions and walking through this model. So and I guess before I move on to this, are there questions about these, like the time evolution of these transactions? Thank you. All right, man, I'm doing a great job at communicating. Cool. Let's go over to the complexity then. This guy thing. Why am I gendering a diagram? That's weird. Anyway, okay. So see, this is why I did not want to start with this, because this is a lot, right? And you'll see these are actually the things like address, identifier, evidence, lock. These are all things that are, if you go into the protobuf spec repo, what is happening? Okay, GitHub. That was weird. Can we go back? That was even more weird. Okay. I just want to point out, like these are the things here, right? So an address in our system is, this thing. So it's a combination of something we call a network and a ledger and the way we actually get to references is through this thing we call an identifier, and then you can go and look and see what an identifier is if you so desire. And an identifier is these things, right? So we have different types of identifiers, and identifiers created out of evidence. So this, the nitty gritty stuff is it should map to this diagram. I think we've been consistent in our language. Apologies if there are some slight mismatches though. But yeah, we can just walk through it. We can start here at the transaction level, and we see if we back up, go back to where I was before I started jumping all around. You can see a transaction is just these three fields. So a field we call inputs, that is a list. That's what repeated means, list. List of something we call a spent transaction outputs. And then there's a field called outputs. That's also a list, and it's a set of unspent transaction outputs. I'm sorry, I'm using list and set not in a formal way. You do have to ensure, right? There's the class, like you can't double spend references. You can't, and this has to be unique outputs or uniquely, yeah. So there are. I'm being very loose with my language here, and I just want to point out that these are like lists, or it's not a single one of these. But the guarantees of repeatability I'm not taking into account at the moment. And then datum. So really and if we think about it, where did I write this? Apologies, I had a memory of writing some documentation for this transaction, and I don't remember where I put it. That was a misstep. But anyway, we can see here we have this transaction, and it takes a list UTXO, or just many UTXOs, many STXOs, and a datum. Right, those are the three arrows pointing into a transaction, and this is just reminiscent of the previous. Right, it's supposed to be this solid line showing the STXOs to UTXOs, kind of similar to what we were doing before. But the question
All right. Sorry about that. I don't know what quite happened there. That was interesting. Okay. So let's just keep going. All right. So it's all this other stuff around that's, interesting. It's like, what is what are, to make a UTXO, you need this thing we call a box value and a datum and an address. But to make an address, you need all this stuff. And you can see it's mirrored up here as well, right? You need an address, an identifier, and identifiers come from UTXOs. So to make an STXO, you have to refer to a UTXO, but how you spend a UTXO, or how you consume a UTXO and convert it into an STXO, is by providing this attestation. And an attestation is equated with a thing that we call a known identifier. So an identifier is simply an identifier is just like what I call the tagged evidence. It's really just it's a hash. It's a unique one-time like consumable thing. That's what an identifier is. And it can be wrapped in an address. And so an address locates the identifier. And then the known identifier is where you reveal what the I forget what the fact is. It's how you tie the UTXO and the STXO together. It's how you actually provide that ref. Oh, that's what it is. It's because how you create an ID, how you create the identifier for a UTXO, the way that is unique, this property of uniqueness and one-time like consumption is incredibly important in UTXOs, because it is the thing that provides, like, it is the power of the UTXO, right? We didn't talk about it in the graph when we were going over it, but how you actually enforce that there's no cycles in it is that you have to generate the IDs every time you create a UTXO. The ID of that UTXO has to be unique, and it can only ever be created once. So the way we do that in practice is that the UTXO ID is actually the transaction ID along with, so it's the ID of the transaction along with the index of its output. And because there can only be one UTXO at a particular index, it's unique, right? You can't have two in one transaction. You can't have two elements at index 1. You can only have one element at index 1. So if I have a transaction ID and the index, the output index, I have a unique tuple, and I can take that pair of data and I can create an identifier from it, or a known. That is what a known identifier is, right? You can always create identifiers, but identifiers may not necessarily be on chain. Known identifiers are, identifiers known to the ledger or known to the chain. And therefore, since it's known to the chain, you can create an attestation that satisfies the lock on a UTXO. So I'm kind of blocking, my head is blocking right now. I don't know how. Yeah, I'll just go move the diagram a little bit. Let's see. Actually, let's just zoom out a little bit. There we go. There we go. I think I'm off it now. Cool. Okay. So we see on the very bottom, there's this lock, right? And a lock is just exactly that. It's the lock that goes onto the UTXO. And a UTXO is then just a reference to some value, what we call a box value, encumbered by a lock. So when I go to turn a UTXO into an STXO, I have to provide an attestation that I know the lock and I can satisfy the lock. That is what the attestation is. And so those things get wrapped up into a spent transaction output. And then these spent transaction outputs are accumulated and transformed. They're the values that are consumed, will be available from the STXOs, can be claimed on the UTXO side. But the fee structure, you might notice that our transactions don't include a fee field. And that is because we are targeting that the fee is any unclaimed inputs. Similar to how this picture, like in this picture, there wasn't a distinct fee. It was kind of just, we had to infer it because we looked at the sum of these two outputs and the sum of the inputs, and we said the difference must be the fee. And that's what we'll have as well. We'll have the fee can go to the miner, or it gets burned. It goes to it just doesn't get claimed. So we don't directly have a fee field. We just need to have the STXOs, and then whichever values are unlocked and want to be claimed by that transaction are claimed by taking the values in the STXO and putting a new lock on it as a UTXO, and then the block producer can take their fee off the top of that. I did get a little fast and quick towards the end. If all we need to take away from today was to reiterate the way that the IO transaction model, like the primary difference between the IO transaction model and the UTXO model, is the inclusion of spent transaction outputs as a primary object. Because the spent transaction outputs can wrap up all of the means by which state must be mutated, or like the contract, the policy that must be satisfied in order to unlock or in order to be allowed to mutate a piece of state. That is what the STXO is. And then we also have the we have the traditional UTXO idea of unique outputs that are ordered in the DAG. And then we also explored this idea of adding additional properties to tokens and how that can make a multidimensional DAG. And then finally, one of the very first things we said was this event DAG is transactions are just one type of event, right? There are, at least as of now, in the Tetra version of our protocol, there will be 3, named events that we are currently targeting, and those are transactions, blocks, and epochs. So that about does it for me. I will pause one last time for any questions, if there are any. Okay. Alrighty. Well, let me see if I can go ahead and pull up this last thing. Well, I want to thank everyone for joining us today, and watch out for us for the next stream. We have a scheduled one in a couple weeks. If there are any questions about this IO transaction model, please feel free to reach out to us. We are, our code is all available on GitHub. We are on Twitter and LinkedIn. You can visit our webpage at topl.co. You can also join our Discord and then also we are streaming every other week on twitch.tv/topltech. Thank you all for watching. Really appreciate your time, and I hope you have a great rest of your afternoon. Oh, there we go. Oh yeah, please don't forget to like and subscribe. Ring the bell. Check us out at you can find more of our links at http://topl.community, topl.community. And yeah, thank you all for your time. Come join us in Discord, help us hashtag Topl the world. All righty, everyone. Appreciate you, and we'll catch y'all next time.